Yeah, welcome. I'm David Pommerenke. I'm professor at TU Graz, Technical University Graz, and I'm in Institute of Electronics, and my area is electromagnetic compatibility and electronics. And today we have an experiment set up, and the experiment is from electromagnetic compatibility. And the idea is to show why an antenna radiates, or even more important for an EMC, how to prevent radiation from an antenna-like structure. But first, let's say, what is an antenna? An antenna is a transducer. It transduces, for example, voltage or current in a coax cable or in a flex cable into radiated fields. Or the opposite, the receive case, radiated fields come and the antenna it captures the field and creates a voltage or voltage and current in some, for example, coax cable or PCB. In EMC, we don't like that. In EMC, we neither like to create antennas which radiate, or we don't like to create structures which receive well. But in general, antennas, of course, a good antenna would radiate all power. So if I give 1 watt to antenna in coax cable, we don't want the power to be dissipated into heat, or we don't want the power to be reflected. And most antennas will radiate directional in one direction. That's not necessary for all antennas that we want that, but most antennas are directional. Antennas can be broadband. For example, you can make an antenna from 500 megahertz to 20 gigahertz, a very broadband antenna. But you could also make a narrowband antenna which only works around 1 gigahertz. These are different design goals. Now, the problem is in EMC, sometimes slots in enclosures, etc. All of these can be good antennas, which we of course try to avoid. So how to avoid a good antenna? Well, one should confine the fields. So if there are 2 wires very close to each other and the current goes opposite, it will not radiate well. If you make it small, electrically small, you're going to see more about that. Small stuff doesn't radiate, and if the stuff is less than maybe lambda 20, then it's really difficult to make it radiate. The other is to avoid resonances. If you have a resonance in a structure, you have suddenly more current because of the high Q factor, and of course then even if the structure is small, it may radiate because you have such a high current because of the Q factor. Okay, we need to look at some very simple concepts on wire antennas. This is mainly valid for wire antennas. And one thing is, of course, here's a wire antenna, and this one is lambda half long. And now if a current flows here, the current must be 0 here. So the current is 0 at the ends, simply because there's no metal anymore. It must stop. And the next is the current is continuous. For example, the current which flows in here must be the same value here. Or if you put an inductor here, the current will be the same. So the current is continuous. Then, if the structure is, for example, lambda half, then the current distribution will be sinusoidal. So the maximum current is here, the minimum current is here, it must be 0. This is a sinusoidal distribution, which is, by the way, also true for long wires, then it's multiple sine waves. Now, if the antenna is short, what we get is a triangular current distribution. Triangulars, of course, if we look at Taylor expansion, is the second order of the sinusoidal. So short antennas we can think about like a linear current distribution. For longer antennas, we have to take the sine wave into account. Okay, another thing is the current which is driven, for example, in this side, depends on the impedance in this direction. We're going to see more of that. But if the antenna is short, we can think about, oh, this thing has a capacitance to infinity and has a capacitance from one end to the other, and this drives the current. It's a reasonable model. But for a lambda half antenna, it's not correct to think about we have a capacitance from here to here. We can only substitute the energy in the electric field by a capacitor if it's electrically small. So actio and reactio are directly bound between left and right. But the delay by the velocity of light is so high that a model of thinking this is a capacitor is wrong. That's a misapplication of the idea that we can express the energy stored in the electric field by a capacitor. This is a wire again, and maybe here's the source. And a good idea good method to get a feeling if something radiates well, we look at the impedance looking left and the impedance looking right, and the current is continuous. So if this impedance is really high, then the source cannot push current. So if this current is low, it must be also low here. because the current through the source is continuous. So let's look at a couple cases. We have antennas, let's say that's lambda 10th as long as not long, and if the source is in the middle, the source is here, or the source is here, which antenna will radiate better. Now here the impedance in this direction and in this direction is the same. It may not be that bad because we have a long piece of metal here. But if we move the source, suddenly it's really hard to radiate in this direction, because this short piece of wire will provide a very low radiation impedance, and it will be hard to drive current. And if we put the source absolutely to the end, this length is 0, so we cannot drive any current. Although this wire is really long, if the source is at the end, it cannot drive in this direction, and because current needs to be continuous, it cannot drive in this direction. Let's look at a couple of situations. We have an antenna. This is lambda long, lambda half long. This is short and thick. What will radiate better? Now, lambda long, we would see a current distribution like this, a full sine wave. And now to drive it, it turns out the drive impedance is actually rather high. So drive impedance may be, let's say, 200 ohm. It depends on the thickness, but it can be driven well. A lambda long antenna will have a slightly higher gain than lambda half. Current distribution here will be like that. It will be a really good antenna, lambda half. So the real part source impedance is 72 ohm. If it's thin, if it's thicker, it gets lower. So now we look at this antenna. This antenna will be very hard to drive current because the impedance left-right is high. But if we have a thicker, we can, let's say this capacitance is larger, or this capacitance is larger. This is electrically short, that's why we can do it. And so this antenna will drive a little bit more than this. So if we rank the antennas, which will radiate best, oh, these are pretty much identical. We give it the A, yeah? This is B, because it's short and thick, and this is C, this is short and thin. Now let's look at a couple more examples. These are related. Here again we moved the source, and it's clear that this will radiate less than that, because this arm is shorter, no matter if this one gets longer. Now what we do here, we keep this arm length the same, but we make this longer. Will be hardly any difference, because the amount of current we can drive is simply limited by this length. And this length wasn't changed. About the same. But now what we do here, this is still electrically small, we put a piece of metal here compared to there. And so this metal may have more capacitance, so the radiation will go up if we put the metal here. But now at this example, we put the metal on this side. Well, it doesn't make a big difference, because the current is simply limited by this length. So here we increase the radiation. This are about the same. They're limited by the short length, and this is again limited by the short length. Let me just summarize here. If we want to avoid antennas, we have to confine fields. We get forward current, reverse current close to each other. We should make structures small, so a long slot will radiate much better than 3 short slots. The same is for a wire. A long wire will radiate, if there's current flowing on, will radiate much better than a short wire. Now, let's go back to the experiments. We have a setup. We have a network analyzer, and we go from 30 megahertz to 200 megahertz. And the output goes into an electro-optical link. This is the link from optical Zuno, which we really like to use. It goes from low frequency to 6 gigahertz. We're only using 200 megahertz. The signal is transferred to an optical signal. The optical signal goes in here. Here's the optical receiver, and it's driven from a 9-volt battery. So we have no cables here. There cannot be a common mode current on the cables. And we drive about 0 dBm. This is a dipole antenna right now. We drive 0 dBm from this direction against this direction. So what we see now here is the coupling from this antenna to this antenna. The antenna is fully extended, and we see below like 50 megahertz. The coupling is not strong because this antenna cannot receive very well, and this antenna is not long enough. And we have a rather flat region here, and we go up to 200 megahertz. Now there are a couple of resonances. We are in a shielded room, but it's not an absorber room. So there are many resonances in the room. Now let's think about the current on the antenna. this is extended as a dipole now, and at the lowest frequency, the current would be sinusoidal, has to be 0. Here, of course, there's no metal, cannot flow, a sinusoidal current. This would be the first resonant lambda half. Now, think about if we reduce the length of one side. So now we reduce the length of one side, and in principle, one could have the same current here. But this side is short, so the capacitance to ground or the capacitance to here is very low. So the current which can flow here is highly limited, and the radiation comes from the total current. So what we see at lower frequencies, the signal is down about 15-20 dB simply by shortening one side. Now the obvious thing is, of course, if we short the other side, the radiation will go down. So what does it tell us? We have to keep in EMC anything which might radiate as short as possible. But if one side is long, the other side is short, it's not as bad as compared both sides are long. So now we went to an extreme. I completely removed one side, the other is there, and we see the radiation is down, let's say a good 30 dB. So in this section, I want to show you something about field confinement, common mode and differential mode. We have our dipole again with a current flowing here, a current flowing here. They have opposite phase. They get received, and this is radiating very well. And now I put the data into a memory trace. Now let's put them to a kind of differential mode. So now both rods are parallel. Both rods radiate a signal, but the problem is they're out of phase. So the signal which comes from here to this antenna is out of phase to the signal which comes from the other rod to this antenna. But the antenna sees both, so they cancel each other. So this structure, which is a differential mode structure, radiates much less. And if we go here, we see the radiation reduced by a good 20 dB over the complete frequency range. Okay, so we are back to a setup where we made the side very, very short, so not a lot of current can flow here. The other side is fully extended. If we put a larger piece of metal on this side, of course we expect that much more current can flow because there's a lot more capacitance. So now we added a top load here for a dipole, what we call the top load or monopole. So we added some metal here. The metal allows more current to flow in this direction. So we have more current flowing this direction. And we see the signal went up by like 15-20 dB. So in this short video, we wanted to explain you how to make antennas or how to avoid antennas. So we started with a full dipole, which is optically driven, so there's no cables here, and the dipole radiates and is received here. Now, the dipole has at lower frequencies a sinusoidal current distribution at its first resonance. Now, if we make the dipole very short on one side, the voltage source, which is in the middle, cannot drive current here because simply it's too short. There's not enough capacitance to ground or to the other side. So the current here is reduced, and the current here is, of course, the same as here, except opposite in phase, because current continuity is valid. If there's less current on the large element, we saw less field. The other experiment is we put both antenna rods in parallel, so they form a differential signal. So they go in this way if you look at the currents. Now the receive antenna will see both from here and from here, but they're out of phase, so the signal is significantly reduced because these two currents cancel. You're the